Welcome back to another video. Today we're going to prove that 5 divide 3 raised to the power of 3 plus 1 plus 2 raised to the n plus 1 by using the principle of mathematical induction. Now let's prove this. And the first thing that I want to do is to let Pn be 5 divide 3 raised to the 3n plus 1 plus 2 raised to the n plus 1 be this statement. And then we start with base step. So for the base step, we need to start with n equals 1. So we're going to have 3 raised to the 3 times 1 plus 1 plus 2 raised to the 1 plus 1, which is 3 to the 4 plus 2 to the 2. Okay, 3 to the 4 is 81. 2 to the 2 is 4, which is 85. And 85 is 5 times which number? It's 5 times 1 and let me think. 17. Okay, actually it's 17 times 5. Okay, so that means that 5 divide this number. Okay, divide 3 raised to the 3 times 1 plus 1 and plus 2 raised to the 1 plus 1. Okay, so that means that P1 is true. So we've just proved the base step. Okay, now let's go to inductive step. So what is inductive step? For inductive step, we have to assume that. P of k is true. It is true for any positive integer k. Okay? And then we have to show that P of k plus 1 is true. Okay? Right? So now we have P of k is true. What do we have? So we can have 5 divide 3 raised to the power of 3k plus 1 plus 2 raised to the k plus 1. This is what we have. Okay? Right? That's what we have. And then by divisibility, we gonna have, so hence there exists an integer k such that 3 raised to the 3k plus 1 plus 2 raised to the k plus 1, which is 3. Oh, I have to use another variable, so we have to use q. So we're gonna have q, which is an integer, such that we have to divide it by 5, so it turns to be 5q. This means that this term right here, has 5 as a factor right now. So we start to show that P of k plus 1 is true. So we have to start with 3 raised to the 3 times k plus 1 plus 1 plus 2 raised to the k plus 1 plus 1. And then we're going to have 3 raised to the 3k plus 3 plus 1 plus 2 raised to the k plus 2. So we're going to have 3 raised to the 3k plus 4 plus 2 raised to the k plus 2. Okay, what can we do with this? So the next thing that I want to do is to try to calculate, this term and this term. So it turns to be 3 to the 4 times 3 to the 3k plus 2 to the 2 times 2 to the k. 3 to the 4 is 81, okay, plus 4 times 2 to the k. Alright, so what do I have to do? The next thing that I want to do is to, well, what do we need? I need to have 3k plus 1 here and 2k plus 1. So I'm gonna have to erase this one. Okay, I'm terribly sorry. So we're gonna have 3 to the 3 times 3 to the 3k plus 1 plus 2 times 2 to the k plus 1. Okay, so we're gonna have 27 times 3 to the, okay, 3 to the k plus 1 plus 2 times 2 raised to the k plus 1. Okay, let me think. So I have 27 here. So I have to partition 27 into 2 and 25. So we're gonna have 25 plus 2 times 3 raised to the 2k plus 1 plus 2 times 2 to the k plus 1. And then we're gonna have, so what do we have right here? We're gonna have 25 times 3 to the 3k plus 1 plus 2 times 3 to the 3k plus 1 plus 2 times 2 to the 2k plus 1. Okay, let me go to here. Alright, so this term right here is now this one here. So let's focus on the last two terms here. I will factorize number 2. So we're gonna have 25 times 3 to the 3k plus 1 plus 2 times 3 to the 3k plus 1 plus 2 raised to the power of k plus 1. And this term right here is 5q. So we're gonna have 25 times 3 to the 3k plus 1 plus 2 times 5q. And we try to factorize number 5. So we're gonna have 5 times 3 to the 3k plus 1. Wait. Okay, let me continue. Plus 2 times q. Okay, we've just shown that this term right here, which is pk plus 1, has 5 as a factor. So we've just shown that 5 divide 3 raised to the 3 times k plus 1 plus 1 plus 2 raised to the 2 raised to the k plus 1 plus 1. Okay, so therefore pk plus 1 is true. Okay, hence what do we have right here? We're gonna have 5 divide 3 raised to the 3n plus 1 plus 2 raised to the n plus 1. Okay, for any positive integer n. Okay, so we have proved that 5 divides 3 raised to the 3n plus 1 plus 2 raised to the n plus 1 for any positive integer n. And that's it for this video.